Hi everybody, welcome back to another IBIPS Education webinar, part of the Occupant-centric Simulation-Aided Building Design series. We are really moving through very quickly and this is us now into the home straight. I'm really pleased to have Farhang Tahmasebi here, who's going to be talking about advanced simulation methods for occupant-centric design. This webinar, like all of the others, is part of the IBIPSA education remit, and we exist to identify education and training needs throughout the building simulation performance community. And we take a very broad definition of what that community is. Really anybody who is working with building performance simulation. So if you think you have a need in terms of education or training around building performance simulation, then do please get in touch if you feel that there's something that we could do to help. Part of what we do is initiating, developing, encouraging and coordinating new education material and methods. So that can be generally in terms of supporting educators, and it can be directly in terms of things like this webinar. And we also like to offer our training sessions to non-members as well as to members. In the work that we do, we post our webinars on YouTube, and you'll be able to see everything online there afterwards as well. And do please take the time to browse through and have a look at some of the content from previous webinar series. There's a whole wealth of content there for you to explore. So in a minute, I'm going to ask Farhang to share his screen and start his presentation. As we go through, you might have questions that you'd like to put to Farhang. If you could put those into the Q&A box, and then at the end of his presentation, I'll put the questions to Farhang. And then if there's anything that we can't cover in the presentation itself, if we run out of time, we'll try and answer them afterwards on the YouTube channel as well. So I think that's all that I need to tell you in advance, and I'd like to hand over to Farhang to start his presentation.
Thank you, Pamela. So I share my screen in a sec.
Great.
Good. Hello, everyone, and thank you for joining in. I am Farhang Tahmasebi, a lecturer at UCL Institute for Environmental Design and Engineering. And today, on behalf of my research team, Muhammad Ouf, Tarek, Liam, Kayu, Amir, Tianjen, and Clarice, I talk about advanced simulation methods for occupant-centric building design. As you may know, this series of IBIPSA education seminars is based on our recently published book titled Occupant-Centric Simulation-Aided Building Design, edited by Liam O'Brien and myself. And this is actually an open access publication that you can obtain from Routledge website. But to put today's webinar in context with the book structure, I would say that the book begins with a number of chapters on fundamentals of occupant-centric design, which sets the basis for our work on modeling occupants and simulation-aided building design and operation. And what I talk about today is based on chapter 8, which is at the point where we bring those fundamental and foundational theories into the simulation-aided design practice. But before talking about occupants, I want to touch on the idea of using BPS, building performance simulation, in the design process. We have rightly argued for years that BPS can help designers test and optimize the performance of their designs cost effectively. And I remind you about this widely used argument that we can make high impact, low cost decisions early on in the design process, decisions that will become less impactful and more expensive as our designs evolve. And that is why we believe that use of BPS to interrogate the energy and environmental performance of our designs early and often in the process delivers more value to the client, occupants, and the society. But let's think a bit more about use of building performance simulation in the design process. Nowadays, we increasingly see such earlier stage shoebox simulation tests done in design studios, which is great. But to play slightly a devil advocate, I wonder if we really need a building simulation to know that, for example, roofs could get the most solar radiation in summer, whereas, for example, south windows in Northern Hemisphere are best for passive solar heating. Perhaps not. And perhaps we should be mindful not to let simulation replace our environmental design insight and the basic rules of thumbs that we have learned in design schools. Of course, simulation can verify our understanding, quantify the performance, and give us good visualizations. But I would say that such simple studies just start to realize the possibilities of BPS in informing our designs. And what are some of these challenges and possibilities that go beyond what we may be able to fully address with the rule of thumbs for environmental design, I ask? And I would say, if you, for example, deal with rather complex building sites or climates that you are not fully familiar with, or when you have specific formal and spatial aspirations for your design, then building performance simulation can play more of an important role in informing your design process. And in a similar way, I want to expand this argument to the inherent complexities of designing buildings for people, the people who will occupy your designs and give life to your buildings and communities. And if we aspire to think more consciously about occupants in our designs and put people's needs, their experience, and their interactions with our buildings at the center of our decision-making processes, then I would argue that building performance simulation has much more to offer. And that's what I want to touch on today. So to start thinking about integrating occupants in the simulation-aided design process, of course, we need to know what kind of occupant behavior models we have. But for that, I refer you to the earlier EBIPSA education seminar offered by Liam O'Brien around 1 month ago, I think, which covered the occupant behavior models. And here I just briefly reiterate that we have some key characteristics of occupant behavior models and would be great to be aware of. These models can be static or dynamic, as illustrated in this figure. They can be deterministic or stochastic. They can be explicitly data-driven or not, or they can be individual or aggregate models. But from this large pool of occupant behavior modeling possibilities, when looking for the right model in a simulation-aided design test, I would say we should consider 2 key questions. And firstly, the question is, in the simulation study that we want to do, should we consider occupants' response to the changes in design? That is, do we need static or dynamic occupant models? And secondly, do we have reasons to subject the occupant models themselves to iterative changes in the process or not? That is, do we want to treat occupants' definition as fixed variables, as fixed parameters, or as variable parameters in our designs, or in our design explorations? And in the next slides, I'll try to make these clearer. So our first possible answers to those two questions give us the simplest and most common way of integrating occupant models in simulation-aided design. And that is use of so-called static occupant models as fixed design parameters. This means you develop your initial model, initial building performance model with inputs such as geometry, construction, infiltration, HVAC system. And let's say for now, basic static models of occupant behavior. And with this model, you can start the iterative process of testing the environmental performance of your design by exploring parameters such as building geometry, construction, and their implications for performance. And this will allow you to make decisions about your design and possibly pick one of the better performing design variants. But to make it more tangible, let's see examples of inputs and outputs in this case. In this approach, we model occupants by estimating the maximum values for occupancy density and say lighting and equipment power densities, and assign daily schedules to these. And as outputs, if, for example, you're interested in, say, space heating demand, you could benefit from such a thermal load balance chart to give you an idea where that space heating demand is coming from. And here, for example, you can see that the specific internal heat gain from people that you have defined has resulted in these green bars. So your assumption gives you this internal heat gain, and this has somehow contributed to your heating demand. And also, even though in this specific case you don't have a cooling system, this has also contributed to the overheating that you can see here on the right-hand side. So these are the obvious implications of your occupancy definitions for your design performance, but there are other things here as well. For example, this rather large mechanical ventilation load that you can see here in blue might have something to do with occupants, because it might be that you have defined the mechanical ventilation rate per person. And so your occupancy definition also influences that huge, potentially huge mechanical ventilation load. And also, for another example, these overheating metrics that we have used here, they are from CIP-CTM 52. They are all calculated based on occupancy hours. So, so all the proportions and ratio and percentages that you talk about and use to benchmark your design are based on actually the occupied hours that you have defined in your schedules. So even in this simplest form, definitions of occupants show themselves in different ways in the estimated performance. And when exploring your design performance, you must be mindful of these assumptions. But you can go one step further and say you want to consider how occupants interact with the building depending on your design. So you pick a dynamic model to represent window operation by occupants. It can be a deterministic one, or it can be a stochastic one. If it's a deterministic one, it may give you a rule to open the windows based on specific indoor temperatures, or it might be a more sophisticated stochastic model which takes a number of indoor and outdoor environmental parameters, and then as the output gives you the probability of opening or closing the windows. So with this, you get a different performance, right? This is this one that we saw before, and this is potentially the new performance when you apply the window operation models. You know, earlier your occupants were, so to say, passive recipients of indoor environmental conditions. So even if the indoor temperature reached 32 degrees, they didn't do anything. They didn't open the windows. But now your model captures their adaptive actions, and as a result, you get less overheating. Of course, they cannot fully resolve it in this design that we see, but you see their adaptive actions. And this means that if you design your windows smaller or larger, or on different facade, it also affects how the building is naturally ventilated by occupants, because your occupants now respond to, let's say, indoor air temperature resulting from your design. And getting back to our second question on integration of occupants in simulation-aided design, regardless if we use static or dynamic occupant models, for different reasons, we may decide to vary occupants-related assumptions in this process as well. And some possible use cases for this, you may test how your building performs under different usage scenarios, the standard-based or empirical, or how different models of occupant behavior impact your simulation results or your design solutions that you get computationally. Here an example from my studies in Vienna. These surfaces represent data-driven window operation models that give you the probability of opening windows based on indoor and outdoor temperature. But you can see that with different definitions of the model, here with and without and with the interaction term between indoor and outdoor temperature, you can get very different responses as to how occupants open the windows when both indoor and outdoor temperatures are rather above, for example, 28 degrees. So that's one possibility that can change your design and that can change your performance to explore. So it's worth exploring. Or if you have a diverse enough data set or a library of models, you can see how your building performs with and for different types of people with different needs and different adaptive behavior attitudes or possibilities. Now we can say that the framework I introduced can be applied to different simulation-aided design methods. And in our book chapter, we have talked in detail about uncertainty analysis, sensitivity analysis, parametric design, and optimization. And but here I just say, if you have seen or used these very helpful parallel coordinates chart very often, but never seen it to explicitly address occupant-related assumptions and parameters, then we haven't yet fully realized the potential of simulation-aided design for an occupant-centric building. And I would say aiming for an occupant-centric design is not only about the design methods we use, but also the specific design objectives that we aim to achieve. Here, a list of possible objectives that we can pursue and support with our simulation studies, namely performance compliant design, robust design, occupant adaptive design, and resilient design. And as I will shortly show you in the next slides, we have tested and demonstrated some of the potentials of these methods in our book. But before getting into the simulation-aided design test that we carried out, let me touch on the specific challenges that our building energy codes pose to occupant-centric design. So we did a study of international building energy codes in terms of representation of occupants, which you can access via this QR code. And one of our key findings of that research was that while we understand that the current performance-based building energy codes, like any other building code for that matter, need to be practical, consistent, and replicable, they are rather limiting, or at least not encouraging, in terms of innovations in occupant-centric design. To explain myself better, most notably, while these codes, as expected, allow you to explore different possibilities in design of building envelope and HVAC system, for example, they expect the same operation scenarios in the proposed and notional building models. So in a way, they tie your hands. And even in most cases, they enforce a specific type of occupancy models. So while we should further research and find ways of expanding the possibilities of building energy codes for occupant-centric design, the current state of the codes, I would say, gives us another reason to delve into simulation-aided design explorations beyond the code compliance procedures. And on that note, in the last part of my presentation, I briefly demonstrate how we tested some of the occupant-centric simulation-aided design procedures in our book. So we set up a parametric shoebox model, allowing detailed adjustments of window and shading elements geometry. And we populated this model with two different sets of occupant models. Firstly, a standard-based schedules, and for example, assuming that the blinds are not used, as this is a very common way of modeling operation of blind in our building energy codes. And secondly, we populated this model in the second option with a set of data-driven stochastic models. Firstly, a stochastic model of presence, which works based on data monitored in office buildings on arrival and departure times, and also stochastic models developed in literature for the operation of blinds and the use of electric lights. So same geometry, same parametric geometry for our test, but two different ways of defining occupants to see how they can differ and what kind of different possibilities they could offer us. And one of the tests that we carried out was on occupant adaptive design, and specifically the potential of demand control ventilation. And as you know, demand control ventilation is a mechanical ventilation method in which outdoor airflow rate is adjusted dynamically based on the number of occupants, for example. And a key finding was that with the first type of occupancy model, the standard-based ones, we did not see much benefit in the application of demand control ventilation. And as we investigated it, we realized that the occupancy profiles based on the standard did not give much variation in occupancy levels for the DC demand control ventilation to be actually very effective. So is it like that in reality? That's something to explore. Do people occupy the buildings like that standard in reality or not? So these opens new questions for us that we need to investigate. But when we use the other model with the stochastic occupancy related models, then we got much more reduction in heating demand and also some increase in cooling demand, as you can see. So this proved to be a case in point for the limitations of the standard-based deterministic aggregate models in testing the potentials of occupant-centric designs. And one of the other tests that we conducted was robust design optimization. And I remind you that in general, by robust design, we mean optimizing a building to reduce the variation of performance under different operating conditions. And here the specific question was if we can make use of our building models equipped with data-driven stochastic occupant models to optimize a fixed shading design such that the lighting energy use and the uncertainty of lighting energy use will be minimized. So to answer this question, we made use of the parametric definitions of a window and shading elements, and first set up a single objective optimization that combined the mean lighting energy use and the standard deviation of lighting energy use, and as estimated actually by 50 simulations of the building. As we have now a stochastic model, so to get the distribution of results, we ran the model 50 times, and that gave us a distribution. So we looked into the average of that distribution of results and the standard deviation of that to answer our question. And the optimization of the shading elements did actually reduce the lighting energy used. And if you are curious, the optimized solution was not to remove the shading surfaces altogether to get the maximum amount of light. So how did this happen? When we looked into the results to verify the reasons behind this reduction of lighting energy use, we saw that in the optimized design, the shades are closed for significantly less time as compared with this model with no shade. And this has resulted, as you can see on the right-hand side, in lower use of lights in the optimized design. And again, further investigation showed us that it was because we had much fewer occurrences of glare in the model with an optimized shading device. And as a result, less events of closing the shade and thus less reliance on use of electric lights. So you see, if you have some reliable occupant behavior models that have some statistical significance and confidence in predicting occupant behavior based on the environmental parameters, you can start to see these more complex relations between the building performance and its interaction with occupants, right? You see the trace coming from shading design, a fixed shading design, to opening or closing of the blinds and switching on the light. You see, so all our models work in a chain to capture the building performance and interaction of occupants and building environmental control systems in a more detailed manner. And we also ran a multi-objective optimization on this test. And here the average and the standard deviation of lighting energy use were our objectives in the optimization. So this meant that we could explicitly make use of the distribution of the results obtained from the Monte Carlo simulation of our stochastic model to investigate the robustness of our design. And we saw that with the specific designs, for example, we could minimize the average energy use, whereas other solutions have been more effective in enhancing the robustness of our design. So in reducing the possibility of unpredictable performances, right? So, or you may have solutions that do rather well in both areas. So these are all possibilities that we have opened up because we have a data-driven stochastic occupant behavior models that captures these nuances of occupants' interactions with building environmental control systems. And stepping back from the specifics of these example tests, I can conclude my talk by highlighting these takeaways from our research. Firstly, I reiterate that considering occupants in simulation-aided design delivers more value to the clients, building occupants and society. And secondly, I would say that even when using the simplest occupancy modeling approaches, such as the standard-based schedules, we can investigate and explore our occupancy assumptions and their implications for building performance and occupant comfort to further inform our design decisions. And finally, I end on the note that with the ongoing developments of data-driven occupant behavior models, we can have many new avenues for simulation and interrogation of our design performance in near future. That is quite exciting. Thank you very much for hearing out my rather short but technical, perhaps, account of simulation-aided occupant-centric design. If there are questions, I am happy to answer.
Thank you very much, Farhang. Do please put your questions for Farhang into the Q&A box, which you should find at the bottom of your screen. We've got one already, but I will start with one of my own. Farhang, I just wonder, in these data-driven approaches, how easy is it to obtain the data in the first instance, and how important do you think it is that the data is relevant or very closely related to the case in question?
Yeah, very good questions, Pamela. Thank you. The cost of measuring indoor environmental parameters and operation of systems is constantly going down. So I think now we have really for very cost-effective solutions to do that, and it is getting closer to our reach. So now we have large data sets, and of course it's a bit disintegrated, so different people have different data sets, and maybe not all of them have come together for researchers who wants to start. But we have more of that, and just a basic search in the publications of the recent years, I think, opens up new possibilities. And also ourselves and some other research teams also have started to publish our data in open access journals. For example, my colleagues and I did once in Nature Scientific Data. So the data is there with the specific descriptors that my colleagues especially spend a lot of time to develop that, so that the data is usable for further research. So there are many possibilities now, I would say. So it's an area full of potentials, I would say, still. And on the second part of your question, I would say, yes, that's a big issue, because of course we are always dealing with new buildings. Every building is unique in itself, and so applicability of different models developed somewhere else on a new context is always a big question. So I would say, simple answer, yes, we need to be conscious of that and do it cautiously. But at the same time, I may get back to this later in the other questions as well. It's commonly, I would say, not that much about finding the exact way that potential occupants behave in a future building, but because anyway we have not much chance, because to start with we don't know the occupants or the future climate exactly. But it's about putting our design into its paces and testing it under different scenarios, under different types of operation, with different kind of people and so on. So I think regardless that we have some concerns about the applicability and scope of different models, we can benefit from them.
Thank you. I think we might come back to that with some other questions as well. For now, can I ask about accessibility of these types of approaches, sort of generally, and also specific tools? So there's a question in the Q&A about whether occupant behaviour simulation platforms like OBFMU are able to be used by researchers with relatively low levels of programming knowledge, or are these very specialist methods that are currently at least only really available to specialists?
Yeah, another very relevant question. Thank you. I would say researchers should not have a problem with that. I myself didn't have much programming background when I started my PhD, but during the process, I also learned a bit, and that was the most fun part of my PhD, to do a bit of coding to process data and perhaps infer some simple statistical models. So I would say for researchers with a bit of effort, it's usable. And as you mentioned yourself, we have a number of different tools now, like OBFMU, or my colleagues at Carleton University, Liam and Burak and others have also, for example, developed a set of occupant behavior, actually, let's say, implemented a set of occupant behavior models for Energy Plus that you can use in Energy Plus runtime language internally. So the whole implementation process becomes more straightforward, although I'm aware that internal integration in Energy Plus has a bit of problem in terms of debugging and those kind of things. But now we have different possibilities also with Python as an external interface. So to sum up my answer, I would say I expect that researchers with a bit of effort should be able to make use of the current developments and build on top of that. And maybe their role will be to push it a bit further to make it more accessible and usable for others. But for practice, it might be a bit of more of a challenge. So I myself still try to let's say, support and improve the use of simpler methods, such as standard-based schedules. And those kind of approaches, we still can do much with those accessible data by writing the most appropriate set of schedules, by testing different kind of operation schedules, or by easily doing some what-if scenarios within the possibilities of those kind of occupant behavior models that we have.
Thank you. And following on from that is another very relevant question, which is what software was used for the simulations in the cases that you were presenting? And then a sort of second part to that is, how do you verify the results of the simulation with real world cases?
Yeah, so the two tests that I showed here are both done in Energy Plus. And I wouldn't say there is any inherent advantage in using Energy Plus over others, but there are things that you might need to be mindful of. And one is the possibilities of coupling the tool with external interfaces, because you have this runtime data exchange that you need to manage. By runtime data exchange, I mean that your building simulation gives you at a specific time step, let's say, an indoor temperature. That indoor temperature should, on that time step, goes to your occupant behavior model. Your occupant behavior model interprets that and decides if, for example, an adaptive action happens or not. And so if you say you open the window, then that already in the next time step should change the situation. So you need to have this runtime data exchange. So that's a key here. For example, Energy Plus in its runtime language allows to do that internally, but also allows coupling with external tools. So that was maybe one of the reasons that we use that. But I imagine that other tools could also do more or less in the area. And The second part of the question I forgot, sorry.
About verifying the results
Oh,
of the
yes, thank you.
simulation in the world.
Yeah, there are many research on this area. I had also 1 or 2 publications with colleagues in Vienna on this, and it's a challenge, of course, but we have developed different metrics. The problem is, so of course you have a stochastic process, right? So you get a distribution of the results, and the reality happens once, and sometimes this comparison is not that straightforward, and you have also this internal this feedback. This data exchange gives you a feedback, as I told you. So again, to really test that, you need to always give the results of the occupant behavior model, give the resulting indoor temperature, for example, to the occupant model to predict it based on the right data. So these are challenges, but there has been some effort done on this. And but I think we should say that when these kind of models started to emerge, I think there was some excitement, as always, about new developments that as if to say just the very use of these more sophisticated models give us more accurate results. But many studies prove that wrong, right? Because the very fact that these models are more complicated and they have so many components and elements and they are random and so on, make them much more error prone. So you need to be mindful of that and do specific tests. And actually, that's what makes it more challenging for standards, right? So I would say, I'm happy to say that I think the time is gone that just by using a stochastic model, your research becomes more important. I think now is time that if you use a more sophisticated model, you need to dig deeper into the simulation inputs and outputs that you're dealing with and try to make something useful out of it.
Thank you. Do you see a role for machine learning in application to occupant-centric building simulation?
Yeah, absolutely. And there have been many efforts on this to understand, explain, and model occupant behavior. In this specific work, we didn't specifically use that, but yes, absolutely. By its definition, I think when you have such, when you have the data on people adaptive behaviors and on the potential contributing behaviors to those actions, be it environmental parameters or social context situation, or anything else that you suspect. If you have that data, I assume machine learning can also be very helpful to explain the behavior that you see and to give you some description and some predictive potential. Yeah.
Thank you. We've had some great questions from the audience today, so thank you very much for that. I'd like to ask another question now, which is about the scale of the simulations that you can use these methods with. So obviously there's a lot of complexity here, and one of the challenges with that complexity will be the computational burden. And do you see, is there a limit to the complexity of a model in terms of the size of a building or the number of buildings in a simulation that you could be using these methods with?
Yeah, another very good question. Thank you. This is actually that one of my PhD students is currently working on. And yes, you somehow also address different aspects of it in your question. Computational cost is a major factor. And the very fact that these are stochastic processes. So if you run things once, it can be an outlier in a way, right? So when you have a stochastic process, you need to run it multiple times and get a distribution. So imagine that instead of one building, is the case for things that sorry, can you hear me all right?
Yeah.
Okay. I would say, sorry, my headset got me confused a sec. So I was saying that yes, you need to to start. You need to run your models multiple times, and if you have a stock level model is already quite computationally expensive, and then you deal with running it multiple times. So this very nature of the stochastic models might make it a bit less suitable for such applications. But on the other hand, there is something else that we need to be mindful of. Again, just jumping into stochastic model and hoping that it improves things is not a good approach, especially when it comes at a high computational cost. In many of these cases, you start, yes, you have a stochastic model that gives you a diversity and gives you a spread of distributions, right? So, but they start maybe some of them, for example, they start from the basic standard-based schedule. You can give a simple schedule to these models, and then they expand it and diversify it in a sense in within specific ranges, so that you have non-repeating profiles, different profiles. But be mindful, if you put them all back together in a large sample size of campus building, they may again aggregate to the same thing. So you have just wasted your time and resources. So you need to be really aware of the characteristics of these models, the behavior of these models, and what kind of diversity they give you. By just having one factor, and then, for example, you have one classic office schedule that has a break during the lunch, if you diversify it, and then you get a bit of cloud around that curve, you might not get much, right? So in the case that we did actually with my PhD student, so what we did was, okay, we had a campus level simulation task in front of us, but we started with one of the buildings. So the building was not a typical building model for simulation, but was a building made within a campus effort. So it was simplified as we normally do those kind of, let's say, stock level modelings. So then again, that becomes the limitations for you. So you don't have as many as thermal zones that you would like. So the resolutions are again compromised there. So with that, we started to test what we can get from a stochastic presence model. And one of the very widely used stochastic models that we use in building simulations, and we saw that with the specific implementation that we did on that study, it actually didn't bring anything, because at the end, it gives us a bit of diversity in the presence profile, and then that again disappear when you put all the buildings together. So it's about how far you capture these complexities of building interactions with system. If it's just about presence, to randomize the presence of occupants in the buildings, maybe it's not really worth it. But if you start to find meaningful interactions of occupants with building system that affect the performance as you are seeking to estimate, then it may become more important. For example, if they play with thermostats and you capture that, if they open windows and you capture that, then things starts to be more impactful.
Thank you. Do you have any other thoughts on how you might do multiple simulations at once, and other ways of speeding things up to get around the computational burden?
I don't know if I'm the exact right person to answer that, but I know that we have now high performance computing possibilities. That, of course, helps a lot. Many universities, for example, UCL has its own high performance computing, and you may find access to similar things in your university or research institute, where you can give them the simulation job the way they want it, and then they have the power to run things in parallel and speed. There are many also commercial cloud-based services, I would say. Yeah, personally, my attitude is to make sure if I'm making things complicated, if it's really necessary. So in many of these cases, it might be that a simpler approach would get you to a better answer even. Yeah.
Thank you. I think that's a great reminder of some of the messages from earlier webinars in the series, particularly from Ardashir Madavi, who was talking about fit for purpose modelling. and not introducing complexity for the sake of it, which from an academic point of view sometimes feels very attractive, but isn't necessarily the right answer.
Yeah.
Thank you so much to everybody for those great questions, and thank you to Farhang for such a great presentation and for answering those questions so thoughtfully and comprehensively. I would just like to tell you a little bit more about what is coming up. So I'm just going to share my screen again and take you through what we are expecting to have in the next couple of sessions. So as Farhang said, we in his slide, we're quite far through now, but we do have 2 left in this series. On the 20th of June, we have the design and consideration for simulation in terms of building interfaces with Julia Day. And that you can see the QR code there to sign up for that. And we have another session on the 26th of June, where we'll be looking at design of sequences of operation for occupant-centric controls with Burak Güney, who's part of the team at Carleton University. So do make sure you sign up for those if you haven't done already. We're currently working on the next series, which will be running in the autumn after a bit of a break over the summer. So keep your eyes peeled for details of that, which will be being released shortly. And in the meantime, we have an extra session which is coming up. It'll be a very busy day on the 20th of June. But we have an additional seminar which is on in situ measurement and model calibration, and that's a case study on the future home, which is based on Energy House 2.0 at Salford University, which is a really exciting opportunity in a very sort of controlled simulation environment that can mimic the real world extremely closely. So do sign up for that and join us to find out more. The recording for this session and all the other sessions are on our YouTube channel, which is called at IBIPSA University. You should get a link from Zoom after this session, which will show you where to go with that. Recordings of each session are usually available by the next day. But there's a whole curriculum in building performance simulation up there now. We have around, I think, 65 videos covering a whole wealth of material. So do please take time to explore some of that. And finally, if you have enjoyed this webinar and the rest of the series, then I'd like to ask you to consider joining IBIPSA as a supporting member to support the work that we do. The supporting members get a subscription to the Journal of Building Performance Simulation. That can either be an online subscription or a print subscription. They have the right to use the IBIPSA supporting member logo, and the fees are really very reasonable. So these fees are unchanged now since 2019, and you can find out more about that at ibipsa.org/membership. So I'd just like to end there. Thank you very much to Farhang, and thank you to the audience for those great questions. I hope to see you again soon. Thank you.
Thank you for having me. It was a pleasure.
Thank you.